This production is brought to you by the University of Edinburgh.
There was a question about, so someone just said, is this a course in mathematics or is it a course in signal processing? That's a really good question. So remember, last lecture I mentioned that would be some mathematics to do in this course, and I went through what they are. So the question is, yes, is signals and systems, or signals and communications, is it a course in mathematics or is it a course in signal processing? Well, let's have a look at that today, because that's, in fact, what I've got my slides on. Let's go back to one of my favourite research problems, and that's trying to improve acoustic speech recognition within an acoustic environment at a distance. So if you've got your phone and you're trying to record this lecture, you've got multipath propagation. So my sound wave is bouncing off the ceiling, off the walls, off any surface, and some of those will reach the microphone and others won't. And what I would like to do is to remove the effect of multipath propagation. And I might also want to remove some noise. So, imagine you go into a big cathedral and clap your hands. Obviously, you're going to get echoes. And there's a certain amount of reverberation within this room, but we don't actually notice it because of a perceptual effect called a precedence effect, which means that basically the ear will take all sounds that arrive within, I think it's about 50 to 60 milliseconds of each other, and group them together. In fact, a small amount of reverberation enhances speech intelligibility. There's one argument that if you go and shout outdoors in a wide open field when it's covered in snow, that it's actually harder to hear someone because there's no reflections, because the snow absorbs all the sound waves. And apparently, if you go into an anechoic chamber where the walls are padded to absorb all the sound waves, then you'll get no reflections and it's harder to understand what people are, it's harder to communicate. Now, the problem I want to try and solve is to remove multipath propagation. So I can consider the room as a system and my speech as an input to that system, and I'm going to take the output and I'm going to manipulate that output to remove that multipath propagation. But the question is, how am I going to model the output of a system? I need to come up, in order to try and remove the effect of reverberation, I need to have an understanding of the effect of reverberation on a signal. So that means, can I predict, if I knew what the reverberation was, can I predict what the output of that system is, given a particular input? So if I played sort of a test tone, maybe if I count 1, 2, 3, can I predict in advance what I should hear once my sound has gone through the room acoustics? That's a good question. And if you can, that helps you actually solve, or try to, that's part of the solution to removing reverberation. So what I'm trying to convince you of is that I'm interested in working out the output of a system as a signal passes through it. So let's go to an example which might be easier to relate to. I know the first year lab has changed over the past couple of years, but my understanding is that part of the first year lab, if you did the first year lab, so I know some of you might not have done the first year lab, but if you did the first year lab, you kind of characterize the frequency response of an op-amp. And you do that by taking a signal generator and applying a signal generator to the input of a circuit, and you will apply a test tone, maybe a 1 kilohertz test tone. And you will measure the output. And probably what you did is you have a sinusoidal input, and as you'll know, you'll get sinusoidal output approximately, unless there's any saturation or clipping. And you tended to kind of overlay those signals on an oscilloscope, and you would measure the ratio of the output signal to the input signal, and that would give you the gain of the op-amp. Would you agree that's something that you've done somewhere so far? I would hope so. So you're measuring a frequency response. So in other courses, you might have come across ODE diagrams or the way of characterizing an op-amp. So the frequency response tends to be flat and then tends to roll off at 20 decibels per decade. That's a way of characterizing a system. So if you know that you put a 1 kilohertz test tone in, you can predict what the output to that 1 kilohertz test tone is, job done. But what happens if you have a more complicated signal? So what happens if I take, say, this op-amp signal here, and I apply a speech signal at the input? Can you predict what the output would be? Now that's going to be an important consideration in any kind of electronic circuit design. If you're designing an audio amplifier, you probably want to try and predict what the output is given the input. You want to know, is your amplifier going to sort of clip certain frequencies and so forth. So what I'm trying to convince you of, given an input signal x of t, I want to predict what the output signal y of t is, given an analysis of this op-amp. So in other parts of the course, if you've done any, you might try and analyze a system by replacing a capacitor by 1 over j omega c, and you might analyze it using your circuit analysis techniques. To be honest, I've forgotten what you've done in the second year. If I'm suggesting you've done stuff and you haven't, don't worry. But you would assume this is an ideal op-amp. You would assume that the voltage differential between the inverting and non-inverting input is 0, and you could calculate what the frequency response of that system is. Okay. So given that frequency response, how do I do it for a more complicated signal rather than just a simple sinusoid? That's an interesting question. Now, what I'm going to try and convince you is I'm going to try and take you through an argument to why we're going to end up doing lots of mathematics. Okay. So the first thing I want to try and convince you of is that this is what's known, this is a linear system. It's a linear system, at least for the range of operation. If you start saturating with signals, it becomes nonlinear. But within a certain input range, the system is linear. That means that, to some degree, well, what linear means is if I put a signal through the system and I measure a particular output, then I take a different signal and put it at the input and measure that different output, and then I come up with a linear combination of a 2 at the input. What I get at the output is a linear combination of the 2 separate outputs. I'll be going over that again later in this lecture. But it's a linear system. Now, linear systems can often be modelled by ordinary differential equations. So, well, you can get the current through that capacitor is the rate of change of voltage across it, proportional to. So if you were to do a sort of current analysis of this, you would end up replacing the capacitor by a first order derivative. And because you've got 2 capacitors, you actually end up with a second order term in your model. Now, in the handout, there's, I imagine if you turn the page, there's a big grey box. On page 30, there's a derivation of an ordinary differential equation that represents that circuit. But if you went through the analysis, or the sort of circuit analysis of this, you come out with a second order differential equation. So system modelling using physical principles, so for electrical circuits using Ohm's law, Kirchhoff's laws, you end up modelling these systems by a linear constant coefficient differential equation. Well, at least we're going to assume for the moment they're constant coefficients. As soon as you get a circuit which has got a variable resistor in or something like that, or a variable capacitor, then obviously that's going to become non-constant coefficient. That's a time varying system. We're going to be dealing with a broad systems of time invariant systems where the parameters don't change. And the next thing we're going to see is that basically complex exponentials are a key building block to analysing these linear systems, and we're going to see why in a slide's time. So complex exponential is e to the j omega t, for example. And Euler's equation would say that would expand to cos omega t plus j sine omega t. The point being that complex exponentials are a combination of cosines and sines. So the question is, why are sines and cosines important? I'm hoping you're already predicting the answer to this. We'll discuss it. But as soon as you hear of cosines and sines, given last semester's maths, I hope you're sort of thinking, right, Fourier series. Okay, so we're going to see why these are fundamental building blocks. We're going to see why linearity is important, and we're also going to see what I call linear signal decompositions, which is basically Fourier series. If you've got a mechanical system, you might model it using Newton's laws. If it's sort of non-relativistic, you can often come out with a constant coefficient differential equation, and that is an expression for that constant coefficient. The summation notation, the sum from p is, this is a capital Peak order. ODE. It's just a compact way of representing it. You'll get used to this summation notation as we go throughout the course if you're not already used to it. You could just write it out in a very long term. You know, the op-amp was modelled by this equation here. So it's a second order differential equation, and you've probably spent a good number of your sort of high-years or A-levels and first year maths solving those. So how do you solve a constant coefficient differential equation? Well, if we assume that the input x of t, so x of t is the input, if we assume that's a sinusoid, then, well, you do two things with solving a constant coefficient differential equation. You solve the homogeneous solution. So you set the right-hand side equal to 0, and you solve for the characteristic equation. So you try a solution y equals e to the lambda t sort of thing. You substitute that in differentiator. You come up with a differential equation, sort of lambda squared plus that term times lambda plus that term. You solve a quadratic, and that gives you the homogeneous solution. Now that homogeneous solution is something I'm going to call a transient. It's a solution that disappears after a certain amount of time. It's like you're in a car and you go over a road bump and you sort of bounce up and down, and that eventually the oscillations disappear. But you also have to solve a particular solution. So that's a solution which depends on the actual input that you've applied. So if I apply a sinusoid, then what is the solution going to be? So anyone know what the particular solution to a constant coefficient differential equation is when the input is sinusoidal?
We will take a function that is equal to a cos omega t plus b sine omega t.
Yeah. So the answer there was we're going to try and take a solution which is a linear combination of a sine and a cos, and hopefully, in fact, I've got this on the next slide, so it's exactly what has just been said. So if we assume that the input is a harmonic function of this form here, so the input is a sinusoid and a cosinusoid with coefficients alpha and beta, you have a guess at the answer. And the answer is of the same form, but with different amplitudes, A and B. Okay? This is not a surprise, because we know this from our analysis with our little experiment we were doing in the first year lab. If you apply sinusoidal input to an op-amp, you get a sinusoidal output at an op-amp. And you've probably done this, I don't know if you've done sort of tuning fork experiments. Basically, there are lots of experiments, physical experiments, where you should be familiar with a concept that if you apply a sinusoidal or harmonic signal to a linear system, you get a harmonic output. So you would substitute this into this equation here, and you could solve for A and B. Now the point being, I'm not going to solve for A and B, we're not going to do a vast amount of that kind of analysis in this course. The point being just that the output is a sine and a cos. So this input here is a very sort of restricted input, and I hope you sort of appreciate, if I put in a more general input, so I could put in, this is a sine and a cos at a particular frequency, omega naught. So omega naught is in radians per second, so it's 2 pi f naught can be in hertz, t can be in seconds, so I could put some numbers in there. But I could put in other frequencies as well. So I could put alpha sine omega naught t, beta cos omega naught t, plus gamma sine 2 omega naught t, plus delta cos 2 omega naught t. And I could have, if I can think of my other Greek letters, I could put sine 3 omega naught t. You know, I can put in a more general signal with multiples of those frequencies. And what do you think when you've got sines and coses all added together and the frequencies are integer multiples of each other? You instantly think Fourier series. So if I can model the input to a linear system by a Fourier series, then I instantly know that my output is also a Fourier series, and it's then possible to work out what the coefficients of the output Fourier series are, so if you like A and B, in terms of the input coefficients of that Fourier series, alpha and beta. So the first thing that shows me and this is living in a frequency domain world, the first thing that shows me is that Fourier series as a signal decomposition is going to become very important. Now, Fourier series only really models, as you know, and we're going to cover this again, Fourier series only models periodic signals. So it will model nice pure tones, or it might, I guess it models like a rectangular pulse which you could come across. But Fourier series is quite restrictive. It doesn't model speech. Speech is not periodic. Parts of speech are. So vowels are periodic, so just imagine saying to yourself E, you can keep going on. That's basically periodic, and anyone who sings will know that certain vocal sounds are periodic. But a lot of speech, a lot of it isn't periodic. So I can't use a Fourier series, so what can I use? I need a more general representation. So that's where we're going to develop the Fourier transform. Now the next most important thing of ordering differential equations is this diagram here. And it's a bit more cluttered than I'd like. It's just the way the formatting's come out. So these are actually two separate diagrams. So when you read this top diagram here, it's probably more separated in the handout because of the figure captions. It's separate to this diagram just below it. So I've already mentioned this. This is what I call the principle of linearity. If I've got a system which I've modelled by an ordinary differential equation, if I apply an input x of a and I get an output y of a, and then well, just remember that. And then if I've got a different signal x of b and I get an output y of b, you kind of remember that. If I then apply a linear combination of those two inputs, xa and xb, so if I apply xa times, that's a multiplication, a coefficient c, and I multiply xb by a coefficient d, and then I add them together, so that's kind of just a little bit of what we call block transform notation, and then I put it through my system, what do I get at the output? Well, I get a linear combination of the individual outputs I would have got had I only applied one of the signals at a time. So at the output I get that coefficient c times ya plus that coefficient d times yb. So a linear combination of signals at the input results in a linear combination of the respective outputs at the output. Okay, so we've got that result there. You can clearly check this all satisfies. If I set c equal to 1 and d equal to 0, obviously the relationship is correct. Okay, so that's what's called linearity. Now what's the point of that? So the point of that is that I could take a very complicated signal. If I can break it down into smaller, simpler signals and work out the output for each individual simpler signal, I can then take the combination of the inputs and take those combinations of the outputs and add them all together, and I've got my final result. So we're going to see how this all comes together. The point being about, we're engineers, right? So how do you solve problems? You solve problems by breaking down a big problem into much smaller problems. You solve each smaller problem separately, and then you put it all back together. Right? Would you agree that's a general engineering principle? That's what we're going to do here. So how do we break down complicated signals into smaller problems? Fourier series and Fourier transforms.
This production is copyright the University of Edinburgh.